Well, thanks a lot, and I'm sorry for not being present physically as was originally planned, and that was unfortunately beyond my control. And I apologize in advance for for occasional coughs. I cannot fight it. So before I begin, I would like to just say a couple of words about my affiliation. It's called Telecom Paris now, which is I'm sorry, these French institutions, they change names every second year. So it's actually one of these network of what they call grandes écoles in France, high technical schools. And since a couple of years ago, it is part of the newly formed Institut Polytechnique de Paris, so Polytechnical Institute of Paris, which unifies a few technical schools, including École Polytechnique, Télécom Sud Paris, and STA and SAE. And it's located to the south of Paris on the new campus in Saclay. So these schools, they have the last year of bachelor and 2 years of master's programs and doctoral schools. So we have around 1,000 PhD students now, around 8,000 master level students, and about 15 master programs. Okay, so at the high level, this talk is going to be about sharing data at a large scale. So there's a growing demand for replication and synchronization at a large scale. And the problem with maintaining desirable level of performance is we need to fight failures and asynchrony. And will try to argue that existing techniques are short in achieving these goals, and we need new ones. And the particular technique I'm going to focus on in this talk is called accountability. So nowadays, a computing system is essentially a distributed computing system. And we have a rise of, in the industry, we have a rise of databases with different levels of consistency and messaging services. And the systems, in essence, try to provide consistency of data, the fact that we share data in a virtually centralized way, even though the data isn't self-distributed. The data should be available, should be able to access it wherever we are, and the system should provide some sufficiently high level of performance. So the major enemies for us are failures and asynchrony. So the system components may fail, and there are no bounds on communication and computing relative speeds. So the interesting question we need to focus first on is what can be solved if we wanted to fight these two adversaries. Well, there's a number of problems we might be interested in, and some of them are sacrificing safety for liveness, and those systems provide eventual consistency guarantees. And here we talk about conflict-free replicated data types or semilinear predicates if we talk about population protocols, etc. Well, there is a very interesting notion of agreement, which is called Lattice Agreement. I will focus on this a bit later in this talk. It turns out that cryptocurrencies can be implemented in a purely asynchronous way and fault-tolerant. Well, of course, we might be interested in solving consensus or implementing a totally ordered sequence of blocks of data like blockchains. Or we can sacrifice it and go for eventual total order. So it turns out that, for example, consensus, one of the fundamental results of distributed computing is that consensus cannot be solved in a fault-tolerant and asynchronous way. And that brings the question of what kind of fault detection mechanisms we need to provide to solve the problems we desire to solve. And by the way, the eventual total order also doesn't have purely asynchronous and fault-tolerant solutions. And I will mention this result a bit later. And by the way, please do not hesitate to jump in whenever you have a question to ask. I will try to keep track of the, we call it raised hands and the chat. Okay, so if we talk about failures, we have major fault models. So probably the simplest benign faults we can think of are crash faults, where a faulty process just simply stops taking steps of its algorithm. And the other extreme is Byzantine fault model, where we make no assumptions about faulty component whatsoever, so it can perform any actions within the model, even though this action is not prescribed by its algorithm. How we deal with faults? Well, the classical way to deal with faults is to prevent them, to mask them, to make sure that the system is correct and available, even though some components are faulty. And the major techniques to prevent faults and to achieve fault tolerance is replication of data to make sure that the data is available and some copies of data are available in the system, and synchronization to make sure that these copies are in a way up to date. An alternative way, or maybe orthogonal way, is detection. So we identify fault originators and make them accountable for their actions. So these two approaches are not contradictory, they're actually complementary. Many systems we want both. And masking failures is comparatively well understood. Detection is less understood. Yes. Okay, so in the outline of this talk, I would just start with giving the context. And the major application we focus on in this talk is replicated services. We start with discussing the problem of fault detection in the crash fault model. And then we'll focus on major topic of this talk is detecting Byzantine faults, detecting and bringing Byzantine parties accountable. And we finish with discussing specific accountability features which focus on a specific application, where we detect, instead of detecting violations of the algorithm, we detect the violation of safety properties, which we impose on the system on the high level. And then we can use this accountability mechanism to reconfigure the system, to make sure that we evict faulty parties from the system and move on. So I would like to say that I'm going to mention the work of the others and some of my work, and this work is done in collaboration with many people. And just mention a few names. So I talk about Rashid Garawi, Petr Duschel, Andreas Heberlen, Thibaut Retour, Sarah Tucci, Joao Becerra, Luciana Freitas de Souza, and Andrei Tankich, and the last three, I believe they are in the audience. Okay, a replicated service. For us, a replicated service is just a collection of servers or replicas of data, which accept requests from the clients and return responses. And the responses should be live. Yeah, the system should be live. Every persistent client should eventually receive a response, and safe. The responses should be consistent. And usually by consistency, we mean that the system execution is in a way indistinguishable from a system running on a single correct server. We assume a message passing system. We have reliable channels connecting every pair of system components. So the channels are reliable in the sense that they introduce no spurious messages, they don't lose messages and don't duplicate messages. And the fault model is going from crash to Byzantine. And we also make some synchrony assumptions. So the degrees of synchrony can go from synchronous, purely synchronous model, where we have known bounds on communication and processing, to partially synchronous, where the bounds exist, but are unknown to the algorithm designer. Or maybe alternatively, we can assume that they only hold eventually, and computation needs equivalent. And the system can be purely asynchronous, and which means that there are no bounds on communication and processing. So the first question we address here is how much synchrony exactly is needed to solve a given problem. And this question was inspired by the fact that some problems cannot be solved in a purely asynchronous way. And that brings the question of the weakest failure detector for a given problem. And this is a classical paper by Chandra, Hatzilakos, and Toueg from the 90s. So in the crash fault tolerant context, a failure detector can be seen as an oracle. It's like a distributed oracle. It gives hints to processes about failures. Every process has an access to its own failure detector module. And the important thing is that the these hints are only depend on the failure part. They don't depend on the current execution. So the failure detectors are completely ignorant of the algorithm the system is running or the problem the system is trying to solve. They only care about who is responsive and who is not. That's why it's a perfect match for crash fault tolerant model, because you can compare failure detectors. You can partially order them. Specifically, you can say that a given failure detector G is weaker than another failure detector G prime if G prime can emulate D. There is a distributed algorithm that collects inputs of G prime, exchange the information across the processes, and emulates the output of D. As a result, we can use this emulation to make sure that every problem solvable with failure detector G is also solvable with G prime. And that naturally brings the notion of the weakest failure detector for solving a given problem P. If it solves P, if it can be used to solve P, there is an algorithm using this information about failures provided by D to solve P. And it's also weaker than any other failure detector G prime that solves P. And this notion of the weakest failure detector brought up a lot of interesting results, which somehow grasp the exact synchrony assumption or the exact information about failures that we need to provide to solve a given problem. For example, there is this classical combination of two results. One result was talking about the weakest failure detector for solving consensus in a system where you have a majority of correct processes. And then it was complemented later by Delporte, Fauconnier, and Guéraoui to show that indeed, if we don't make any assumption about the environment, we can devise the complete failure detector for solving consensus. What is this failure detector? It's actually a combination of two failure detectors. One is called a quorum failure detector, and it's denoted by sigma. So, intuitively it produces a set of processes which a given process trusts. Yeah, and we call them quorums. And every two quorums which are output by any two processes at any moment of time in the system should intersect. Yeah, and eventually only correct quorums are output. Yeah, on the safety side, we make no decision unless a quorum is consulted. This is the usual application of this failure detector, and it turns out that it's the weakest failure detector to implement a storage system in an asynchronous system. The other component of this weakest failure detector for consensus is omega. It's a leader election oracle which outputs the process identifiers, and eventually it guarantees that eventually the same correct leader is output everywhere. Somehow it complements the liveness part of consensus. Eventually the leader will decide for all. So many algorithms which solve consensus are leader based. So the leader proposed the value, and if the leader is not suspected to be faulty by sufficiently many processes, the decision is taken. Okay, so naturally this combination of sigma and omega gives you the weakest failure detector for consensus. Intuitively, this combination might remind this folklore CAP theorem about consistency, availability, and partition tolerance, which was coined by Brewer about 20 years ago in an invited talk, I think, at POTSI 2000. And essentially, it says that if you want to guarantee consistency, the data should be indistinguishable from a single correct server processing this data, and available, meaning that persistent clients get responses to their requests, which could be either modifying the data or consulting the data. These two properties cannot be combined with partition tolerance. Any two pairs of these properties can be achieved, but not all three of them together. And this is not surprising that for consensus, well, Gilbert and Lynch later translated this CAP theorem in a more formal way into the impossibility of implementing storage if you don't have a majority of correct processes. So in a way, sigma fixes partitions. Sigma makes sure that the system is never partitioned. So if you can implement sigma in your system, it means that you can sort of fix any partition eventually. Okay, and it turns out that if you just ignore the problem of partitioning, if you want to guarantee eventual consistency, we can like instead of making sure that you agree all the time, you eventually agree on the sequence of data transitions or state transitions in your implemented system, then omega is sufficient. And you can actually show that omega is indeed necessary for solving this problem. Yeah. So it's we have instances of consensus. Eventually, all these instances guarantee the safety and liveness properties of consensus, but up to some point, it only guarantees liveness. So the omega guarantees that eventually the leader stabilizes and makes sure that all the eventual instances of consensus are safe and live. Okay, so this was a comparatively recent result showing that this is sufficient and necessary, and the necessity part was actually interesting because it was leveraging the tools devised for the original consensus algorithm, but with some lightweight modifications. Okay, so this is what I wanted to say about crash fault tolerant failure detectors. And if you want to learn more, I would probably advise you to go to the survey, one of these ACM computing surveys on the failure detector abstraction by Freiling, Geraoui, and myself. And now we go to the major topic of this lecture, which is how we detect Byzantine failures. And here we need to understand that Byzantine failures are fundamentally different from crash fault failures, because when we try to detect them, we essentially try to detect deviations from a given algorithm. So we cannot do it in a no ignorant way. We need to know what the system is supposed to run. Otherwise, the very fact of Byzantine failure is not clear. So there is a rich literature on detecting crash faults. There is much less literature on detecting general Byzantine faults. So there was some generic accountability approaches when proposed either in the context of specific systems or in a more general way, which is a peer review system, or some specific fault detection, which were trying to detect failures beyond crash faults, such as muteness failures, so we sometimes call them omission failures, or Byzantine failures, but for specific problems. The problem of consensus, because consensus for a very long time and still is considered to be one of the most important problems in distributed computing. So I will try to argue that accountability must be considered to be the first-class citizen in distributed algorithms. So, but for this, we need to understand what faults are detectable and what is the cost of detection. Here I'm referring to a couple of papers, one of the comparatively, well, both of them are comparatively old, but I think there is a growing interest in coming back to these questions because of the advent of blockchains, which is essentially Byzantine fault-tolerant protocol, which is supposed to scale in a very harsh environment, but it is very hard. So in a way, we need to use all the help there is, and the accountability that could be one of the tools we may want to use. So now we refine the model a little bit. We assume that messages can be signed. This is inevitable in this context, because if you want to produce accusations against a misbehaving party, we must be able to prove it. And we must be able to provide a proof which can be verified by the third party. And for this, we need some way of signing the messages, and this in a way that these signatures cannot be forged. If a process performs an action, and a typical action a process may perform in the distributed algorithm is to send the message. So this message should provide an irrefutable proof that the message has been indeed sent by this process. We still assume that the system is asynchronous. It's always beneficial to assume as little as possible about the system, so that you can, at least for the lower bounds and impossibility results, that's the best strategy. So in this sense, execution is just a sequence of events. Yeah, since there are no timeouts, the sequence is just a sequence of events produces an execution. An event is essentially a tuple of the event originator, process identifier, the set of inputs, which could be either application inputs or received messages, and the set of outputs, which could be either the application output or a message sent, or set of messages which the process sends in this event. And a distributed algorithm is just a collection of automata The automata maintains a set of messages that the process can generate. Well, each process is assigned with its own automaton, and the set of possible inputs it can receive, we call it TI for termination terminal inputs, and terminal outputs, so the set of outputs it can produce, a set of states it can maintain, the initial state, and the transition function. And here we assume that the transition function is deterministic. We focus on deterministic algorithms. So it's actually a very interesting question, how to account for probabilistic algorithms, how to detect deviations from a distribution of actions. So what is fault detection in this sense? Imagine that, just to give you the intuition, imagine that we have a system of 4 parties, and there is a node C which receives inputs from A and B. The inputs are below 10, and it should produce the sum of these 2 inputs and send it to D. So in case everything is fine, yeah, we receive 7 and 4 and sends 11. In case it is Byzantine, it may send a value which does not correspond to the inputs. Yeah. In this case, we would like to the remaining correct parties to be able to detect that C is misbehaving. Okay. So given an algorithm A, yeah, so we assume that we know what the algorithm C is supposed to run, and a set of faults to detect. I will elaborate a little bit later what we understand as a fault. So the fault is a deviation from A in an abstract sense. Our goal is to make sure that the fault in this fault class occurs. Yeah. A correct node should output a list of faulty nodes. Yeah. In a way, we build an extension of algorithm A. Yeah. This extension does exactly what A is supposed to do, plus it detects failures. Yeah. So our goal of the fault detection problem is to find a generic transformation that maps any algorithm to its extension with this additional property of fault detection. So what is an extension? Extension is essentially also a tuple. It's an algorithm. Yeah. So the inputs and outputs should be compatible. So the terminal inputs should be the same. The terminal outputs should be a superset of the original terminal outputs. Why a superset? Because it should produce the same output plus fault detection, fault indications. And there are some surjective mappings from the set of inputs to the set of outputs, and this mapping should somehow be compatible with the transition function. So whenever we have a set of inputs and set of states, sorry, so and set of outputs. So it makes sure that whenever we have a transition in the original algorithm, we have a matching transition in the extension. So in this sense, the extension should be close to the original algorithm, so we can map every execution of the original algorithm to the correct execution of any execution of the extended algorithm to the correct execution of the original. And it's important that the node, if it's correct in the extended execution, it should also be correct in the produced mapped execution of the original algorithm. So it's in a way we cannot introduce more failures than originally happened. Okay, what is a fault instance? Yeah, I said that we have fault class. A fault class is just a collection of fault instances. So it's here we need to specify the algorithm, of course, yeah, with respect to which we detect deviations. We need to specify a set of correct nodes in a given execution. And we need to specify the set of suspects. Yeah. So the set of suspects should contain at least one faulty node. Otherwise, it makes no sense. There's no failure, or there's no suspicion. Why we need a set of correct nodes when we specify a failure? Because the detectability really depends on who is correct. Depending on who is correct in the system, we have different abilities of detecting failures. So, for example, if we have, we come back to the original example, we have 2 inputs and the incorrect output. Yeah, if these guys are correct, yeah, only these guys are correct, we are not really able to detect who's faulty here. Okay. So now, if we want to quantify how precisely we can detect failures, yeah, we need to specify who is suspicious. For example, if we have 23 received from C, we know for sure that 23 cannot be a correct value because the inputs, it's a sum of two values of less than 10. So here, either we suspect that C is incorrect, or maybe C has received incorrect inputs. And we don't really know who is responsible for that. So here we need to specify who can be suspected. Okay. So now the fault detection problem is, given a fault class, find a transformation that maps any algorithm A to its extension such that we have a completeness of fault detection. So if indeed in the predefined fault class F, we have a fault which occurs, at least one correct node will permanently output at least one faulty suspect in the set of suspected nodes. Yeah. So eventually correct nodes do not output each other. Yeah. So we never suspect, well, there's no suffix, infinite suffix of your system execution in which a correct process is permanently suspected by another correct process. But occasional mistakes are okay because the system is asynchronous. It's in a way, it's inevitable. And correct processes should agree on the set of permanently output faulty nodes. Okay. So given this problem of fault detection, we might ask ourselves, what is detectable? Which fault classes are detectable? So in a way, if we detect all, we describe all general fault instances in one figure, so we can find a boundary and demarcate a borderline between fault classes, faults which are possible to solve and faults which are impossible to solve. So it turns out that, of course, there are non-observable faults. Yeah, non-observable in the sense that it's misbehaviors, deviations from the algorithm. They do not affect correct processes at all. It happens somewhere in the cluster of faulty nodes which only communicate with each other in a way. You can also have ambiguous fault instances where you cannot raise any detection, any suspicion without a risk of suspecting a correct process forever. Okay, here we better not suspect anybody. And finally, we have commission faults. With commission faults, intuitively, it's a fault which is an action which can be actually brought down to the originator of this action, which obviously matching the input of the process and the output of the process indicates that the process is misbehaving. And omission faults. Well, omission faults, this is closer to what crash fault detectors are trying to achieve. They try to detect omission behaviors, the behavior in which a process does not perform an action it's supposed to perform. So if we ask the question what it costs to detect different classes of failures, so we have two variations. We can either require agreement. Sometimes, actually, in the context of broadcast protocols, I think this sometimes is called totality. The fact that whenever someone suspects a process, everybody should eventually suspect him. Yeah. So there are different costs, and it turns out that, for example, for omission failures, achieving totality or achieving agreement detection, it is quite costly. And notice that these costs are per instance of misbehavior. So this is quite an overhead. Intuitively, it's a linear overhead with respect to the system size, because typically the fault bounds, which is F here, is a linear factor of the system size. Okay, so what is the main conclusion we can draw from this slide is that fault detection in the general sense is costly. You just want to detect misbehavior of a process with respect to some abstract algorithm we are given, it may cost a lot of extra messages. And this gives the link to the what we call application-specific accountability, which is not as ambitious. It doesn't really care about arbitrary deviations from a given algorithm. What it cares about is the safety violation. And in a way, it's a much more pragmatic approach because, yeah, from the application's perspective, we want the system to be correct. We don't care who behaves or who misbehaves. We want the system to be correct, and that once we detect who is correct, once we detect a safety violation, we can bring it back to the originator. Sometimes, also some algorithms. And this observation has been made quite some time ago. So there was, for example, there was a Byzantine fault detection mechanism already ingrained in some early consensus algorithm. And lately, in the paper published this year at SCDCS by Civit, Gilbert, and Gramoli, this was made explicit. It was the notion of accountable consensus was introduced. And it's coming from a very simple observation that most algorithms which implement consensus in a Byzantine fault-tolerant system are based on the following simple idea. So whenever we want to make sure that, for example, we want to resolve conflicts between two parties proposing some input A and B in a state machine replication system or consensus, we need to choose one of these two proposals. Yeah, this proposal should go through a quorum, and the quorum should intersect. Yeah. So the underlying assumption is that intersection of every two quorums used to decide on a value should intersect on the correct process. At least two of these servers should be correct. At least one of these two servers should be correct. But if it happens that both of them are faulty, in this case, it may happen that two processes decide different values, we can actually detect it. And because every solution to consensus also brings the corresponding quorum. So we know who was responsible for this solution. And this intuitively, this accountability mechanism is already there. Okay. And as soon as we detect a failure, we might want to reconfigure the system and move on. Yeah, because if we detect that someone caused safety violation, we may want to reinitialize the system in a way, evict the misbehaving parties, maybe introduce new parties, and move on. And this is called reconfiguration. So the interesting combination which we're going to explore is how to combine accountability and reconfiguration, specifically in the asynchronous way. And the traditional approach to reconfigure the system was based on consensus, which is inherently not asynchronous because consensus, as we already know, does not have asynchronous solutions. And the consensus-based reconfiguration was used even for the systems which were not using consensus in the first place, for example, for storages. In a way, the slashing mechanism in Ethereum is also using accountability for reconfiguring. So whenever we have a misbehaving party, we are able to evict the undesired miner from the blockchain system. A fair ledger protocol was proposed for doing consensus. And then lately, the long-lived blockchain by Ranchal, Pedrosa, and Gramoli was also using consensus. However, if we don't use consensus for maintaining the state of the system, and this is the case for storages or cryptocurrencies and other kinds of systems, we may want to do it asynchronously. And here, instead of consensus, there is another interesting abstraction, which I'm going to discuss in more detail, which is called Lattice Agreement. So Lattice Agreement is, in a way, it's a form of agreement, but instead of making sure that we agree on the total order of changes in the system, what consensus provides, the participants learn an ordered sequence of something, of blocks of data, or it can be changes in the system configuration, or can be changes in the system state, whatever. So and we use consensus for doing this. In Lattice Agreement, we have a partially ordered set, and the participants of the system learn ordered values from this partially ordered set. So they don't agree on the exact sequence. Different participants can have different sequences of learned values. But what we guarantee is that these sequences include only elements which are comparable with respect to this partial order. For example, if we look at this example, one process can jump to the final state from the very beginning, and some of them can go through a number of intermediate stages. And this is okay. It turns out that this form of agreement is sufficient for solving many problems, in particular for reconfiguring the system. So formally, we have a notion of a lattice, which basically is just a set of values which has a partial order and a well-defined least upper bound operator. we call it a join operator. For any set of elements in this partially ordered set, we have the least upper bound element. And we also assume that there is an origin value, which is basically the initial state of the system. Well, the most popular lattice there is a set. Basically, it's just a set lattice where every element is a set of values, for example, a set of natural values. The partial order is just defined by the inclusion operator, and the union is the join operator, and the empty set the origin. Okay, so this is one of the major tools we're going to use to reconfigure the system, because the system configuration can also be seen as a set of updates. Yeah. For example, we can also add a remove operation, which can be represented as adding a specific minus v element there, and here we assume that this set is a set of whole numbers rather than natural numbers, also negative. Another example is a max register, which is actually essentially built on top of a totally ordered set. Here the join operator could be the max of two values, and the partial order is just less or equal operator. And this is very useful for the context of implementing, for example, timestamp values, a value which is provided with the sequence number. And this is a very common approach to implement a storage system, where whenever you read a set of values, you always choose the value with the highest sequence number. And this is exactly where we can use max registers. The important feature of lattices is that the lattices compose. So given two lattices, we naturally get a composed lattice, which is also a lattice. So there's a composition of partial orders is a partial order. The composition of join operator is a join operator. And as I said, for example, n max registers can be considered as an element of a lattice. And this is the major approach to implement an atomic snapshot, for example. Yeah, so atomic snapshot is just in one snapshot operation, we get the atomic view of the system state. And actually, the first paper which introduced the problem of lattice agreement was actually done in the shared memory. And it was showing that the two abstractions, lattice agreement and atomic snapshot, are essentially equivalent. And what we're going to use here, we're going to use message passing implementations of this abstraction of lattice agreement. So what is lattice agreement? So we have a lattice, which is a set of values, a partial order, and a join operator, for example, a set. We make sure that processes propose values to this abstraction. It's just a data structure which is distributed. Processes propose values, elements of the lattice, and learn values. And we guarantee that eventually, well, not eventually, it's actually safety property, all learned values are comparable. So every learned value should be somehow based on the inputs. And we require that learned values should be joins of proposed values. Yeah, we cannot learn something which has never been proposed. Notice that it's just a join. It doesn't have to be a single proposed value. So there's no perfect agreement there. And on the liveness side, we guarantee that every value proposed by a correct process eventually appears in the learned value of every other correct process. Okay, so this notion of lattice agreement is very interesting, because unlike consensus, it can be implemented asynchronously. It can be implemented in an efficient way. And when I say efficient, I typically mean responsive. Yeah, so it can be done in a finite bounded number of interactions with the system. Yeah, so it only depends on the actual message delays in the system. And it turns out that it's actually perfect fit for implementing reconfigurable systems in the asynchronous way. So what is reconfiguration? And we said that typically we assume that we have a set of replicas and set of clients. Clients access the data. So clients can come and go. We don't control really the set of clients. However, we try to make sure that the set of replicas is somewhat manageable. Yeah, so it's expected to provide some consistency guarantees to the clients. And if it turns out that we suspect some of the replicas to be faulty, yeah, after observing its behavior for a while, or for example, for raising a suspicion using a fault detection mechanism, we may want to replace them with new ones. But we want to do this in a way that is transparent to the users, to the clients. The clients they're not really affected by this reconfiguration. Okay. So the asynchronous reconfiguration, which was introduced by the Dynastor system, well, already quite some time ago. This asynchronous mechanism can be naturally grasped through the notion of a configuration lattice. So it's an abstract lattice. Every element there is just the element of some configuration lattice. We don't really specify what it is, except that we know that every configuration element should include the set of members, which is a set of replicas used by the clients for storing the data, and a set of quorums. And these quorums should satisfy some consistency and availability properties, which is important for the safety of the object we want to implement at the end. And maybe some other attributes we don't really care. Okay, one example is just a set of updates. So the element of this configuration lattice is just a set of updates. Well, for example, here we have +1, +2, +3, and -2, meaning that, okay, we have introduced process 1, 2, and 3 at some point, and then we actually remove process 2. Well, process, when I say process, I mean a replica here. Well, the partial order is just the inclusion order. The join operator is just the union. The members are all added and not yet removed elements of the configuration, and the quorums are all majorities of the members. This is one example. And here, to make sure that the system is correct, we need to make some assumptions about the environment. And one typical assumption is to say that all two quorums of the active configuration, the configuration which has been introduced but not yet revoked. Well, so there are some very well-defined notion of revoking and configuration, should include a quorum which contains only correct processes, and every 2 quorums should be the same. Notice that if configuration is obsolete, it has been replaced by a strictly higher configuration, then we don't make any assumptions about this. So we can introduce the notion of a reconfigurable object, assuming that the object itself can be grasped through the notion of a lattice. We take a composition of the two. And then we solve the lattice agreement on this composed object. And this lattice agreement on the composed object gives us exactly the configurable object assumption. So here, whenever we want to change the system configuration, we propose a new configuration in the same way as it's done in the lattice agreement algorithm. Okay, in every configuration, update results in a join of proposed configurations. So notice that processes can actually propose different configurations concurrently. And in the asynchronous way, using the lattice agreement mechanism, they're able to reach some form of agreement about what is the resulting configuration. Okay. Every update on the object state should be installed in the quorum of each candidate configuration, and this is part of the algorithm. Okay. So whenever we decide on a new state, all preceding configurations become obsolete. And whenever we decide on some specific configuration, all configurations which are proper subsets of the decided one are obsolete, and the adversary can do whatever it likes with it. But we guarantee that we should guarantee that as long as the configuration is under consideration of the protocol, it's active and not yet installed, or once it's installed and not yet obsolete, it should be in a precise way correct. Okay, so this is what we mean by an available configuration. And this approach, given that it's very abstract, we have different, we don't specify really the object lattice and the configuration lattice, can be used for implementing multiple objects in the reconfigurable way, such as max registers, sets, atomic snapshots, conflict detectors, very interesting abstraction for contention of our algorithms, the commit adopt abstraction, the safe agreement, the cryptocurrency, which we call asset transfer, etc. And there are crash fault tolerant implementations of this, and also Byzantine fault tolerant. Yeah, so we can introduce reconfigurable abstractions in the Byzantine fault tolerant way. And well, this is about reconfiguration, but how we use this reconfiguration, who actually brings this reconfiguration requests and how we use it. Here we have one example, which we I think, one of the few examples of reconfigurable objects, which are also combine reconfiguration and accountability. And this is the paper which I'm not going to talk much about, because this is the paper which Luciana Freitas de Souza are going to present in the session which is coming next, I believe. So just a high-level idea is that we talk about lattice agreement object, with some abstract state of the object we want to implement. I don't know, whatever it is, cryptocurrency or whatever. And it has the common case execution, which guarantees safety and liveness under some assumptions about the environment. So we propose values and we learn values, and these learned values are always ordered, and they are joins of proposals, and every correct client would eventually learn a value. But if something goes wrong with our assumptions about the environment, the environment doesn't keep the contract we make with them, we can detect safety violations. For example, we can detect the instances of values which are learned, but their values are not comparable with respect to the partial order of the ledges. We might want to accuse a specific replica, so I could raise an undeniable evidence of the replica misbehaving and update it. So we update the configuration by introducing new replicas and revoking the compromised ones. Okay, so this goes beyond just maintaining fault tolerance. We also provide accountability and reconfiguration. And we can run it in a single system and completely transparent. Okay, so on a high level, what we're talking about? Talk about the feature of making the system components accountable for their actions. And here, well, we raise the topic of self-healing distributed systems, which combine fault tolerance and accountability. So it's not purely new. This feature is present in many existing systems, especially in the industry. But I think there is some interesting theory behind this too. So we want to make sure that consistency and availability are provided in a regular model, in a model with under regular fault assumptions. And if these fault assumptions are not satisfied, we detect the misbehavior of faulty parties and reconfigure the system if indeed the consistency of the system as a whole is violated. So notice that here we're not ambitious. We're not trying to detect any instance of misbehavior, any deviation from the given protocol. We only care about deviations which affect the outputs of the system. Okay, and there are multiple dimensions there. We can use the accountability features, for example, for improving resilience of a protocol. And a couple of recent papers we've shown this for example, for consensus, what we call fast Byzantine consensus, or Byzantine broadcast, Byzantine reliable broadcast. We can actually improve resilience by introducing some form of accountability in the system. Yeah, we can tolerate less failures. We can improve consistency in the system with decentralized trust. Here, it's a completely different topic where we have multiple processes, and each process has its own idea about who to trust. There's no centralized quorum assumption. There are some decentralized quorum assumptions, and using this decentralized quorum assumptions, we can actually raise some suspicions about who's faulty and who is not. So you can improve consistency in this kind of systems, and we can introduce accountability as incentive for behavior. And here there's an overlap with a game theoretic approach to algorithm design, because the fact that every action, or at least every dangerous action, the action which affects the system state, the system safety properties as a whole, is accountable, may actually stimulate you to behave. Okay, so this is a very comparatively new topic. I think there's a lot of questions to consider. I didn't really touch upon the cost of accountability. So I think if you want to start looking at this, you can look at one of the older papers on Byzantine fault tolerant, Byzantine fault detection problem, or on the more recent one on Polygraph, the consensus algorithm with accountability, where one of the major questions raised was the question of the cost. But still, we don't understand how much it costs in general and what are the trade-offs with other complexity metrics. Okay. What synchrony assumptions may introduce to accountability? Yeah, how we can detect failures. For example, for crash fault-tolerant algorithms, it's obvious that under different synchrony assumptions, different faults can be detected. A very important question is privacy and how we can use the modern tools in cryptography to achieve different forms of accountability. And yeah, there are many algorithms which try to optimize performance by using some fancy cryptographic tools, but these tools may make your system less accountable. One specific example is threshold cryptography. If you want to sign a message by sufficiently many processes, you may want to use a constant size threshold signature, which just says that sufficiently many processes signed this message, but it doesn't reveal the identities of these processes. And might be very hard to detect later who exactly signed equivocating messages. Well, there are other aspects which I didn't mention. For example, how we deal with probabilistic algorithms, how we make the detection more lightweight, maybe by using stochastic accountability and stuff like this. So with this, I will finish, and I'll leave you. I hope we will have some time for questions. So again, this is a joint work of many people, and some of these people are here. And I thank you for your attention, and I will ask for your questions. Thank you very much.
Any questions?